Sorry.
Good afternoon, everyone. Now we are entering in the second session of the day. It gives me immense pleasure to introduce and welcome our eminent speaker, Professor Renu Chugh. Am I audible to all of you?
Yes, ma'am.
Okay. Thank you. Renu Chugh is Professor of Mathematics at Department of Mathematics, Maharshi Dayanand University, Rohtak. She has been teaching PG classes for more than 34 years. She has guided 2 postdoctoral, 30 PhD and 32 MPhil students. She has more than 200 research papers published in reputed national and international journals. She participated in 3-week Leadership for Academician program sponsored by the Ministry of Human Resource Development, MHRD, Government of India, organized by University of Hyderabad in participation with Monash University, Melbourne, Australia, from 11th Feb to 23rd Feb 2019 at University of Hyderabad, India, and 25th February to 2nd March 2019 at Monash University, Melbourne, Australia. Her area of specialization is non-linear functional analysis, fuzzy mathematics, and fractals and chaos. She received award as one of 100 Women Achievers of India in the category of education by Ministry of Women and Child Development, Government of India, and felicitated by Honorable President Shri Pranab Mukherjee on 22nd January 2016. She received prestigious INSA Award on 29th December, Indian National Science Academy in IISER Pune. She received the award Empowered Women Developed Society by Minister of Haryana, Shri Manohar Lal Khattar, on occasion of Haryana Growing Haryana, organized by Jagran Forum on 12th August. She was felicitated for teaching research and administration on occasion of Teachers' Day on 5th September 2021 by Chancellor and Governor of Haryana and Vice Chancellor MDU Rohtak. I think she is a lady of awards. Now I welcome Professor Renu Chugh on the board. Please, ma'am. Over to you, ma'am.
Thank you so much, dear Dr. Kumar. Really grateful to AICT for Department of Mathematics, Rajeev, head of the department. Good afternoon, dear participants. You have to bear this problem. We have some electricity issue in the department. You have to bear it. There may be some inconvenience. Am I audible?
Yes, ma'am, very much. You are audible loud and clear, ma'am.
Now it's okay. Yes.
And screen is visible?
Yes, ma'am.
Is screen visible?
Yes, ma'am. एकता मैम कोई प्रॉब्लम आ रहा है? आपका माइक शायद म्यूट, आवाज नहीं आ रही है आपके माइक की भी। इट्स ब्रेकिंग, मुझे लग रहा है मैम नेट कनेक्शन वीक है। आई एम राइटिंग इट ऑन चैट बॉक्स मैम प्लीज।
Am I audible now?
Yes.
Okay,
Yes,
okay,
ma'am.
okay, fine. That. So, dear participants, as I told you, please bear with us. There is some issue with electricity. So we are going to start with the presentation, Fractal Geometry, Kiosk Theory, and Fuzzy Mathematics. And we will, first of all, we will discuss about Kiosk Theory. This is actually presentation is in 3 parts. First of all, we will discuss about Kiosk Theory, what is it all about, its background and history. And then in the second segment, we will discuss about fractal geometry, right? And what is a fractal basically, how it originated and what are the applications of this fractal theory. And in the third segment, that is the last segment, we will discuss about fuzzy mathematics. That is what is fuzzy all about, what is fuzzy logic and its background and its engineering applications also we will discuss about. And so start with this presentation. We are going to discuss mathematical modeling, dynamical systems and chaos, and then applications of chaos theory. And because different maps are used in, so we will discuss about some different maps, and then fractals, origin and history, and then applications of fractals, and then fractals relationship with symmetry, and then why fuzzy and fuzzy sets and fuzzy logic later. Why we all, what is the base of this chaos and fractal theory? Why we all need it? Because our nature is really chaotic. This is a slide is all about, this is from a article from Cosmos newsletter by Alfredo Metter. That is nature really chaotic and fractal, or we just imagine it? And in this article, if you read this article, it's a very, it's a good article. And it helps us to perceive that reality is a function of how we slice and dice the physical world, right? So why we need to study fractals and chaos? This is the question. Because generally people believe that in this nature, in this geometry of nature is centered on simple figures like lines, circles, polygons, spheres, quadratic surfaces, and so on. But actually this is not so. We don't have everything in nature which depends on the symbol figures of geometry. That is, for example, if you see, can we describe the structure of animal and plants? And what is the shape of mountain? How can we describe with the help of classical geometry? Not possible. Even the network of veins, even the cardiologic system, all these can't be described by the classical geometry. So we need something more than the classical geometry. And these fractals and chaos are the answers to these questions. Because other objects in nature, which are complicated and irregular, they are, even their dynamical behavior is complicated and irregular. Suppose if we see the heart and brain waves, you must have checked in ECG, right? If you have a sudden fibrillation, that fibrillation causes sometimes failure of the heart. So very small initial change in that leads to very big change. And even if you see the stock market, there are ups and downs in financial market, or even our social behavior. Sometimes we are sitting quietly, but someone says to us something and we are otherwise behavior hamara ekdam change ho jata hai. We are very angry sometimes, we are emotional sometimes. So that is also social behavior is also our social behavior change, ups and downs are there. So another question is, how do we model this turbulent weather, cascading waterfalls? For all these queries, for all these questions, we have fractals and mathematical chaos, these are the appropriate tools for this. So these are new frontiers of science, and they play nowadays significant roles in science, medicine, business, textile industries, and also in other areas. And also you have that, you will see in the next slides that their link is very strong. They are very much connected. And as fractal geometry is that type of geometry which describes the chaotic system we find in nature. And the most important reason behind this, because it has increased, if you see the number of papers, they have increased in number, exponentially increased. Many people are working in these areas. So because this is non-linearity is there, and we can help this calculation is possible with the modern availability because we have now computers available. This is a paper, or you can say from Chaos, Research, Fractals and Fuzzy Logic, from Stereotypes to Reality and Consequences for Medicine. Try to read this paper, good paper. In this paper, it is clearly mentioned that we have that it is not this chaotic structures as clouds, weather, forecasting, these because can't be expressed in terms of mathematics. So chaos theory helps us, and fuzzy logic teaches us that there is no such thing as certainty of action. So you can go through this paper. It's a good paper. Another thing which we, how we realize the importance of this chaos theory more in these COVID scenario, from 2-3 years, because in the last 2 years we are facing this reality, and then the scientists understood its importance of chaos theory because it is very well connected with COVID-19. If you see this, the first part of this slide, this is a video, the math behind why we need social distancing. If you see this video, it's clearly gives the relationship between mathematics and COVID-19. And similarly, other article, if you see this article, mathematical modeling and epidemic prediction of COVID-19. So with the help of chaos theory, we can even predict and how it, you can this, because this is an infectious disease, how it grows exponentially, we can take care of it. And we can take the preventive measures accordingly. So we have another, this is a video. This is the pandemic is chaos, and how chaos theory helps explain the weirdness of COVID-19 pandemic. And it's tells us about the pandemic, chaos, and coming to terms with uncertainty. Because the main connection between chaos, fractals, and COVID-19 is that is the uncertainty. Even fuzziness is uncertainty. That is why these theories are very much important in the current scenario. So basically, mathematical modeling is used in the taking care of this COVID-19 symptoms and other measures which we can take, because mathematical modeling can compute a more realistic picture of the infection rate of the novel coronavirus that causes COVID-19. And with the help of this, how we can better prepare, how we can better prevent it. And this is, we also tried to analyze some dynamical behavior of COVID-19 with the help of in this paper. We tried some novel epidemic model and tried to analyze and control this chaotic behavior, how we can have this analysis. In this, this model describes the whole impact of corona preventing measures. Especially this paper is about corona preventing measures on the spread of epidemics with the help of time. And in this, we have used bifurcation diagrams as well as time series analysis has been done in this. And now another story, which was a study which was published in Canada's Epidemiological and Research. This highlights that mathematical modeling of infectious disease actually is a tool to study how diseases spread and how we can anticipate the future course of an outbreak. And even we can help guide public health planning and infectious disease control also. So using these models, we can prepare our health system for the better preparation can be possible for the projected number of patients. And similarly, we can evaluate and adjust public health measures. So mathematical modeling thus is experimentally delineated phenomena by means of mathematics, because mathematics is involved. With the help of mathematics, we can model these, and then we can use the difference equations or differential equations, and then we can have solutions of these. And the model actually derives from the Latin word modulus, that means small measure, right? And mathematical models can be used to represent just about everything in the real world. They can be used. And so is actually idealized representation or example that real life phenomena can be modeled with the help of these mathematical equations. But with the help of these equations and graphs, pie charts, tables, line graphs, chemical formulas and diagrams, we can these mathematical models. Now, because dynamical system is very much related with the dynamics. So what is dynamics? So dynamics is anything that moves, changes, or evolves in time. And the term actually dynamics is the time evolutionary process. What is dynamics? Actually, it is time evolutionary process. And it has been very much important because we are dealing with non-linearity everywhere. In nature, linearity is not possible. Most of the things are non-linear in nature, and the dynamical system is moving or changing in time. So we have to use these dynamical systems. Am I audible?
Yes, ma'am, audible.
So we have that non-linear dynamic systems, or you can say weather, neurons. They are because often chaotic, unpredictable, yet their behavior is not random sometimes. So dynamical system is the system in which a function describes the time dependence of a point in a geometrical space. And for this, we need Kiosk theory. And Kiosk theory describes the behavior of certain dynamical systems, that is, those systems whose state evolves with time, but they are highly sensitive to initial conditions. There are basically two types of dynamical systems, linear and non-linear. Linear, you very well know what is linearity. That means ratio of input to output is same. That is linearity. And what is non-linearity? That means that are not linear. That means ratio of input to output is not the same. I give always a simple example that if you आप पौधों में पानी देते चले जाते हैं तो growth of the plant is non-linear. बिकॉज जितना पानी देंगे जरूरी नहीं उसकी ग्रोथ होगी, दैट इज नॉन लिनियरिटी. सिमिलरली आप मेडिसिन खाते हैं तो जरूरी नहीं ज्यादा मेडिसिन खाने से आप जल्दी ठीक होंगे, इट विल गिव यू साइड इफेक्ट्स आल्सो. सो वी हैव नॉन लिनियरिटी एवरीवेयर. दैट इज व्हाई दीज Kiosk, fractals, fuzzy mathematics are very important subjects. Another thing is in dynamical system, they are whether they are discrete and whether otherwise they are continuous. Discrete means time variable is discrete, right? It is in clicks. It is not continuous. And that discrete dynamical system uses iterative maps, difference equations. Similarly, continuous dynamical system uses differential equations. For these models, we use differential equations, and for discrete difference equations and iterative maps are used. And we have that, if you see here, Kiosk theory and the importance of social distancing during the pandemic. Why we have that? Basically, we have nonlinear phenomena is dynamical system phenomena is that a particular action always results in a reaction with the same intensity. This was given by Isaac Newton. But now these theories, if you see in the nature or in the other nonlinearity, this is not possible. That every particular action always results in a reaction with the same intensity. It can be of higher, it can be of lesser intensity also. So that means their reaction will be maybe higher, maybe lower. So it can be difference. It can't be same. This is a quote given by James Gleick that which refers to this, what is chaos. That is, this new science called chaos offers a way of seeing order and pattern. We have in the system nonlinear phenomena, we have disorder, but this theory helps us to C order and pattern, where formerly only the पहले क्या था आपका random था, erratic थे, unpredictable. In short, the chaotic had been observed. Now we have that, if we see the certain dynamical system, this is a good book, Kiosk and Dynamical Systems. In this book, you will find various applications of these dynamical systems. So what is, if you see real life examples of dynamical system, you have space shuttle in orbit around the Earth, you have water that moving in the glass, you have ecosystem with completing species, the nervous system, if you see, even the expanding universe, if you say solar system, this list is endless. They are all dynamical system, moving of a pendulum. And so they are always moving or changing in time, right? Maybe discrete, maybe continuous. So that's why these are important. And scientists and researchers try to predict where the system is heading, where it will ultimately go. Earlier, your prediction of weather was not accurate. Now it has come close. It's approximately accurate now. So it was actually the French mathematician Henri Poincaré who gave the idea of this, and he is known as the father of nonlinear dynamics, right? He has, you can say, proved so many results regarding this dynamical system. That's why he's known as the father of nonlinear dynamics. He said actually continuous systems in connection with this international competition, which was held in the honor of 60th birthday of King Oscar. And here he studied this continuous systems. And then he, while studying the study of dynamics, he found it convenient to the continuous flow of time with a discrete analog, right? And the further contributors, they were A.M. Lupino, and then because Lupino exponent, Lupino stability results are very much used in Kiosk theory given by Lupino. These are the quotes. I skipped that. Another, this is a good book, Integration of Ecosystem Theories, a pattern. Here it suggests that this Kiosk theory is concerned with unpredictable courses of events. They are irregular, they are unpredictable timed evolution of many nonlinear complex linear system, which has been named Kiosk. And how to handle this Kiosk? We need this Kiosk theory. So Kiosk is the science of wonderments, surprises, confusions of the nonlinear and unpredictable, right? What will we say? This is the science of surprises, wonderments, you will say confusions of the nonlinear, unpredictable, and it teaches us to expect the unexpected. So basic property which chaotic system have, that's sensitivity to initial conditions, means causing large divergence in the prediction. But actually this divergence is not infinite. It oscillates between bounds. So Kiosk theory is a mathematical approach to modeling patterns of nonlinear, non-independent behaviors of dynamical systems. And the word Kiosk came from the Greek word chaos, means gaping void. It originated from the Greek word chaos, means gaping void. So it means a state of disorder and confusion, right? And dictionary meaning, literal meaning is, that is a state of things in which chance is supreme. So three things, that is, it came from the Greek word, originated from the Greek word chaos, and it means that a state of disorder and confused. And dictionary meaning is a state of things in which chance is supreme. So the definition is, we can say that that is the dynamical system which have these properties: nonlinear, determinism, and sensitivity to initial conditions. So chaos is a science of the global nature of systems, or a nonlinear phenomena of nonlinear dynamical systems, which changes over time based on its current situations. And how it originated, basically it started with the works of Henri Poincaré. He was a French mathematician, late 19th, who extensively studied topology and dynamical systems, and he explained, it may happen that small differences in the initial condition may produce very great one in the final phenomena. And then during the 1960s, our scientist Edward Lorenz, a metrologist from the MIT, he also attempted to explain the Kiosk theory. And later on, Edward Lorenz also discovered one of the Kiosk theory's fundamental principle. We will also discuss about that. That is butterfly effect. So how the birth of Kiosk, how it happened? So it all, you can say, attributed to Henry Poincare. And because what happened, the King of Sweden had offered a prize to anyone who could answer the question, is the solar system stable? But actually it was proved by Poincare. He got this prize in 1887 for his pioneer studies of three masses, that is Sun, Earth and Moon. And then regarding this, that is the solar system stable? And then he gave this some result which were the basis of Kiosk theory. This is the picture of Henry Poincare. He studied the three-body problem, and also he found that there can be orbits that are non-periodic and yet not forever increasing nor approaching fixed point. Edwin Lawrence, you can see the picture. He was an American mathematician and metrologist, basically, and he was the first main from where the Kiosk theory in actual shape came. And he was inventor of the strange attractors notion in 1963. And he discovered that minute variations in the initial weather parameters led to grossly divergent weather patterns known as, he coined this term, butterfly effect. This is the book of reference from the book, right? If you see here how it started, that Edwin Lawrence, about the story about the Edwin Lawrence in 1960, when he was studying about the weather models on the computer in MIT. And when he tried to approximate it, he was doing some programming regarding the weather details. And later on, he found that when I midway shut down and then again started and put that values, the approximate values, it immediately amplified. And the entire system was out of whack. That is the from basic of Kiosk theory. It's again that about uncertainty principle, because its base of this is also uncertainty. So uncertainty principles, he wrote that the uncertainty principle prohibits accuracy. Therefore, the initial situation of a complex system can't be accurately determined, and the evolution of a complex system can therefore not be accurately predicted. Again, I think we have already discussed about Kiosk theory and COVID-19. I skip this. So this about what is all about this butterfly effect. It is a big phenomena. That means it comprises a long chain of successive small events. Lawrence provided an input in his simulation exercise, and even this pandemic, you can say this is also like a butterfly effect, because you have seen that if you have some persons infected and they go to the crowded place, immediately you have this butterfly effect that it can affect a large number of populations. So this pandemic is also really like a butterfly effect, because it has an we have this in economy also. We have seen in education system, job market, social stability, process of globalization. This butterfly effect is everywhere. Another thing we have that this is from an article in the Predict by Nathan Pigel, and it says about, or it describes about the dynamical systems with apparent randomness, irregularities, and laws which are sensitive to initial conditions in mathematical terms. And we have to find the underlying pattern in a chaotic complex system, which could range from constant feedback loops. So we chaotic situations we encounter every day. Tea, coffee can be chaotic. Beans can be chaotic. We are sometimes We have ups and downs in our lives also. Our weather is chaotic. So everything around is chaos sometimes. So chaos theory is the study of deterministic difference or differential equations, right? And that it is in such a way, it generates time paths that look random sometimes. So nonlinear phenomena, because the chaos, fractals, and fuzzy, they are all related to nonlinear phenomena. This is all, they are all about nonlinear phenomena. So you can find out the nonlinear phenomena. You can find out in plasma physics. You can find out in solid state physics. You can find out in optical fibers, in biology, in fluid dynamics, in chemical kinetics. So chaos usually occurs during nonlinear phenomena. It is in the real world, we have weather patterns, we have meteorites, lightning, earthquakes, financial markets, even populations of some species, the heart, the brain, economic system, social and natural systems. This is chaos in the real world. Even in stock market, you can see, even in the fashion designing, in the human body, in social sciences, in engineering, in robotics, in circuits, as a literary theory, or even music, we have this chaos, applications of chaos theory. So chaos is a science of the global nature of systems, and that determines order in the randomness and unpredictability that exists in the natural systems. So in coastlines, mountains, clouds, galaxy of leaves, heart, rhythms. So chaos, and so as it is well said by Margaret Whitley, that chaos is the final state in a system's movement away from order. So, and these, I skipped this, but it has various applications like population biology, synchronization, control, finance, particle swarm optimization, image encryption, secure communication, pseudo-random number generation, network evolution, neural network model in physics, chemistry, engineering, and so on. So these are basic 5 characteristics: nonlinearity, determinism, already we have discussed, sensitivity, initial conditions, order and disorder, and long-term prediction is almost impossible. So chaos is a field of study in mathematics with applications in several fields of science and art. And even it has various applications in population biology. We have already discussed finance, image encryption, secure communication, neural network model, network evolution. This is all about the man who studied stock market. It is Jim Simmons. Actually, he was a mathematician. Later, he shifted to stock market, and he applied his mathematical knowledge even to that stock market. And he was the richest person in the US. And his math, because he was math genius, he used his knowledge of mathematics to make and got incredible gains in the stock market investment. So it has, you can see various applications. In NASA's also discovery, then we have atomic force microscopy, pattern formation in chemical and biological systems, controlling chaotic heartbeats, or you can say even impact mechanics and offshore engineering and the chatter of cutting tools. So mathematics of low dimensional chaos theories. Now, if you read this paper, it's a good paper. It's 100 years old. It says that. And in this, we have various applications have been given. Another is a paper in the journal. This title of this paper is Overview of Chaos Theory, Applications in Information Security Systems. If you are interested about other applications and information security systems of chaos theory, you can go through this paper. It has given, you can say here it is written that this chaos theory have applications in information security, Another, the paper in this paper, it has been mentioned, another point, important point has been mentioned, that there is a close relationship between Kiosk theory and cryptography. So more attention, that is why, is given to chaotic systems, because it has various applications in this image cryptography, in the digital communication systems, compressions, networks, encryptions, modulations, information security systems, cryptographic and stenographic systems. I skip this, we already discussed. So butterfly, it is well said about butterfly effect by J. Escher, that you have heard of the butterfly effect, right? That is what is butterfly effect. That is, if a butterfly flaps its wings at just the right time in just the right place, suppose in the another city in the London, and then we have that effect is another city in the US. That is the butterfly effect. That is a very small effect, gives rise to a large effect in the other part of the world. That is the butterfly effect. So that means it can cause a hurricane thousands of miles away. That is all about Kiosk theory. That is, a tiny change in a big system can affect everything. So we have kiosks everywhere, even in our hot cup of tea, already discussed, flow of water, downstream. These are all chaotic. So it is not simply disorder. We will discuss about some practical applications of Kiosk theory in actually human behavior also. In you can say society also, we have applications of Kiosk theory, because we can apply this in organizational behavior. We don't go in much detail. There are in business management, creating high performing teams, this Kiosk theory behavior, because Kiosk is all about human relationships also, decision making. In this, some maps, which usually there are studies, there are logistic maps, Q-deformed logistic maps, delayed logistic maps, standard maps, 10-type maps, Ricker maps, Hannon maps, basically the difference equations which are used in these models. And difference equations, if you see, I will show this. Basic difference between differential and differential equations is that differential equations are examples of continuous dynamical systems, whereas difference maps are examples of discrete dynamical system. I hope everyone is listening and I'm audible. Is it okay? Am I audible and visible? My
Yes,
screen is
ma'am.
visible. Is it
Yeah,
okay?
yes.
Are you listening or sleeping? Everyone, please.
Listening, ma'am.
Madam, we are
Okay.
listening.
I hope all of you are listening and not sleeping. Next part, we will discuss about the, just show you the slides of these different maps. Because I have skipped, I have to take the other two parts. I have to discuss about them also. This is actually the equation of the logistic map. Mathematically, it can be written as xn plus 1 is rxn, 1 minus xn, where xn is a number between 0 and 1 and r should be greater than 0. And suppose we have a population model. Usually this, because it was given in 1845 by Pierre F. Verhelst, and usually it is used for this population dynamics. Here, one-step feedback machines, two-step, these three-step, four-step machines are used. Another map, a very good map, which is used in dynamical systems and Kiosk theory, is of tent map, right? And then if you see here, this is a chaotic orbit of the tent map, or CoWeb diagram is there, its orbit, and it is about 200 iterations, and it has sensitive dependence on the initial conditions on the closed interval 0, and tent map is topologically transitive, and it has chaotic behavior in the closed interval 0, 1. Another is Ricker map. This is the definition, rather equation of this Ricker map. Xn plus 1 is xn er minus xn by k. Again, you can see their pictures. Another important thing which is used in Kiosk theory is about bifurcation. Doxima, I'm supposed to finish by 3:15. Is it? Yeah. Okay. I will try to. So bifurcation is a scientific way to say something which splits in two branches. And that means that patterns bifurcate. It is about bifurcations. If you see the tree में आप देखते हैं ना, trees में bifurcate होते हैं, leaves फिर से bifurcate हो रही हैं. So they can become complex very fast, leading to bifurcation, cascade, and chaos. So this is a picture in Logistic Map, how we have bifurcation diagrams. So what about the, I finished this part, Kiosk theory. So it has deep roots in science. It emerged from questions on stability and predictability of systems. It is based on solid mathematical insight, and which is elevated by the development of computer technology. So because chaos is a rule rather than exception, so there are various discoveries yet to be made. Another part, now, second part of this, my presentation is about fractals, because we have fractals everywhere. If you see, I will show you with the help of pictures, you will find out that fractal is everywhere near us in nature also. But B. Mandelbrot, he is known as the father of fractal geometry. He says that the number of distinct scales of length nature exhibits not only simply a high degree, but an altogether different level of complexity. The number of distinct scales of length of natural patterns is for all practical purposes infinite. So now we will discuss about what is a fractal. These are two videos. I have checked these videos. You can listen to these and watch these videos. One is about fractals and the art of roughness. Another is God a mathematician? Fractal geometry of nature. Very good videos. Try to watch it if you get time. You will really be, you can say, feel divine. So now what is a fractal? Fractal is the class of complex geometric shapes that commonly have fractal dimension. You must have this geometrical dimension. You have already integer dimension, but all the things in nature, they can't be measured by this topological dimension. They have fractional dimension, right? It's not only integer dimension, it is fractional dimension. And this concept was first introduced by the mathematician Felix Hausdorff in 1918. So they are distinct from fractals. Actually, they are figures or shapes or objects which are different from the simple figures of classical or Euclidean geometry. So already we know only in the classical geometry square, line, circle, sphere, and so on, the triangles. But we will show you with the help of pictures. I will show you that it's not all about these things only. And Mandelbrot was the first to point out that fractals could be an ideal tool in applied mathematics for modeling a variety of phenomena, from physical objects even to the behavior of stock market. These are YouTube videos. I've checked these videos. You can take a screenshot of this. That is the edge of infinity, Mandelbrot fractal zoom, eye of the universe, Mandelbrot fractal zoom. Even these, what's so special about the Mandelbrot set, number filling, and Fibonacci numbers hidden in the Mandelbrot set. I will show you also how these are. The picture of B. Mandelbrot, the father of fractal geometry, from his book, The Fractal Geometry of Nature. He wrote that our geometry is often described as cold or dry. Because reason क्या है वहाँ पे? क्योंकि आपकी जो classical geometry है, that can't describe the shape of a mountain, cloud, coastline, or tree. Because clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line. These are pictures of some contributors of fractal geometry, because H.V. Koch, we have Koch curve, even Koch snowflake, F. Sierpinski, he gave Sierpinski's triangle, Sierpinski's carpet. George Cantor, you know very well that is founder of Cantor set theory, you know very well. Then B. Mandelbrot, who gave the concept of fractal geometry, Felix Hausdorff, then again P. Fetu, and then Karl Mencher. Because often in nature, we find, if you see the broccoli, you see the cauliflower, coastlines, mountains, rivers, you will find that there is something common in that. That is self-similarity, right? That means they are pieces of each other, but each other, that means broccoli, if you see, अगर आप एक एक पीस तोड़ते हैं, अगर देखें उसको, तो क्या लगता है आपको? सेल्फ सिमिलैरिटी है, वो स्मॉलर पीस भी उसी तरह है, बट स्केल डिफरेंस हो गया. तो इसी तरह से आपका जो फ्रैक्टल है, that should be defined in terms of fractal dimension. So what we have, the properties of fractals are, it has a fine structure and arbitrary small scales. It is always, mostly it is irregular at local level or global level, and self-similarity is mostly approximate or statistical. And another important point is fractal dimension is always greater than its topological dimension. This is the main point. If you calculate the fractal dimension of an object, always it will be greater than its topological dimension. So fractal, most cases, is defined recursively, right? It has a recursive feature. So it is based, because it is based on equations which undergoes iterative processes are used, right? So we have, if you see this video, I checked this video, fractals hunting the hidden dimension. In this video, it was that mysteriously beautiful fractals are shaping the world of mathematics and deepening our understanding of nature. You may not, sometimes you don't know we are, but fractals are everywhere in us also, rather, I must say, around us, in us. The air even we breathe, it's all about fractals, because they have irregular, repeating shapes, are found in cloud formations, tree limbs, broccoli, mountain ranges, even in the rhythm of, you can say, human heart, even in the neurons of brain, all we have. So it has a mathematical basis. If we see fractals, it should have mathematical basis. It has fractal geometry has wider vocabulary. It has symmetry there. It has structure there, but sometimes they are random, they are chaotic. And also another feature is that there the order is governed by mathematical rules. An important another feature is fractal dimension. This is, you can say, fractal geometry, beginning of new era. In this, it has been mentioned, this article, this has been mentioned that no one will be considered scientifically literate tomorrow who is not familiar with the fractals, right? Very major statement has been made, very important statement has been made in this, that no one will be considered scientifically literate tomorrow who is not familiar with fractals, because human body, lungs, brain, vesicle systems, branches, tree branches, all have fractal properties. And it can be applied to various fields of medicines, neurobiology, pathology, molecular biology, cardiovascular systems, because they have to study, if they want to study the heart rate of individuals in different time scales, they need some different theory, not the classical theory. So this helps, this fractal theory, geometry helps us in finding out that various diseases, how the heart rate is going, because they form a complex fractal pattern, right? Even if you see in the last slide, because to measure the infiltrative margin of the malignant tumor, to assess the tumor angiogenesis, and to assess, because fractal geometry is very helpful in medicine. These researchers has very much found results which can be applicable in this medicine. And there, but some limitations also are there. But still it is one of the important tools to explain true geometry of nature. and it deals with non-integer dimensions, which is known as fractal geometry. So mathematical fractal is based on an equation that undergoes iteration and a form of feedback based on recursion. We need iteration, we need recursion, and these beautiful and complex looking objects are generated by simple mathematical processes. And this word fractal is coined from the Latin objective fractus, and that means to break, to create irregular fragments. So that means if a piece is broken from either of these, the part still resembles the whole. जैसे मैंने आपको अभी बताया कि आप ब्रोकली लें, कॉलीफ्लावर लें, एक पार्ट भी तोड़ेंगे तो वो जो छोटा पार्ट या बड़ा पार्ट वो resemble करेगा. They will resemble. Symmetry will be there. Maybe scaling may be different. So it must have a fine structure at arbitrary small scales. Self-similarity must be there. Two irregular, approximately self-similarity, not the exact, but it must be at least approximately. And basically there are two irregular, even coastline, if you see, coastline that is very irregular. आप उसको measure नहीं कर सकते उसके dimension को, but with the help of fractal geometry, we you can say we convert this non-linearness into linearity and then find its dimension. So it must have a fractal dimension, and fractal dimension is always greater than topological dimension, which must have a simple and recursive definitions. This is the definition of fractal dimension, or how it is calculated. It must have dimension should be log n by log s, where n is the number of pieces of an object and d is the dimension of the object, and s is the scaling factor. For example, if you see here, I will show you another with the help of Cantor set, because Cantor set is basically a classical example of fractals. As you all know, Cantor set, you study this all about in graduation and 11th, 12th also. This, I will show you the picture, because it is very important. Cantor set has many important consequences and applications in the field of set theory, topology. Even I will show you. This is the picture of Cantor set. If you see here, just middle third, then remove its middle third, then again we have the close interval, and you should see its picture. So it is actually constructed from a unit interval 0, 1 by a sequence of deleted operations. You delete, and it is properties at self-similar, fine structure. It is obtained by recursive procedures. If you see, it has all the properties of a fractal. Dimension of f is in fraction. I will show you its dimension. And fractal dimension of f is greater than its topological dimension. Nowadays, we have variants of Cantor sets also. We have also some papers on this variants of Cantor sets also, and we have tried to find out its dynamical analysis. It is the picture. Another is Koch curve. Very classical and important fractal is Koch curve, and it is made by repeatedly replacing each segment of a generator shape with a smaller copy of the generator. This is a picture of Koch curve. If there is a simple iterative process using this, how we get this. So I skip this is middle 1/6 curve. Koch island, if you see, if its dimension is 1.2619 log 4, scaling factor is 3 here, number of pieces 4. And then another important fractal is Sierpinski's gasket. You must have heard about Sierpinski's line, Sierpinski's triangle, and then we have even Sierpinski's carpet is also there. It was introduced by great Polish mathematician W. Sierpinski's in 1916. You must have read about Sierpinski's line in topology also. So he gave this basic construction of the Sierpinski's triangle, how it is created. If you see this triangle, then we have 3 parts. Again, if you see this picture, again we have then again this recursive process is operated. Then you have this, and again we will have have this, and its fractal dimension will be 3, 2. See, it has scaling factor as 2, half, because it is divided into half here. If you see here, again it divided into half. So its scaling factor is 2. That's why its dimension is 3 copies, but scaling factor is 2. So log 3 by log 2, that is 1.585. Similarly, you have Cantor set, the dimension of Cantor set also. See here. That is dimension of Cantor set, as you know, this 0.63, this fractal dimension. Another important, that is burning ship fractal. If you see its shape, it is in the form of burning ship. It seems that. And another is Lupino Fractal. It is also constructed by this, you see, and you can check its stability and chaotic behavior by Lupino exponent. And then Julia set, if you see, this is the picture. I skip these details because it's the third segment of my, that is about fuzzy mathematics. You should see the pictures of Julia sets. These are pictures in another orbit, that is SP orbit. This is very important fractal, that is Mandelbrot set, with which this B. Mandelbrot, he gave this idea in 1975. He introduced the Mandelbrot set, and he gave this, that it consists of all parameters for which the Julia set of a function G is connected. So it has become very popular because its aesthetic appeal is in identification, music, visualization, medical beauty is concerned, where we have this set. You can see this pictures of Mandelbrot sets, and it's these pictures. It's the computer programming. We can have these pictures. What is the Mandelbrot set? Is the Fibonacci numbers hidden in Mandelbrot sets? Right? I will show you. See this Fibonacci spiral. Sequences 1, 1, 2, 3, 4. The last two numbers, 1, 1, 2, 2, 5, like this, 3, 5, 8, like this, 1, 1, 5, 8, 13. So 1, 1, 2, 3, 5, 8, 13, like this. So we have, they are, because in nature they have, we have in the flower Fibonacci sequence example is that also. In nature, we can find in steel also, in chambers of Nautilus shell also, you have Fibonacci pattern is there. And if you have a bulb, that is also a three-dimensional fractal, if you see it. Right? It was given by D. White and Paul in 2009. Another is multifractal. If you see its shape, it is again a system of fractals. It is the generalization of fractals, which are not characterized by a single dimension, but they have different dimensions. And because they have continuous spectrum dimensions, so they pattern multiple scaling rules rather than one global scaling rules. Basically, classified fractals, they have exact self-similarity, especially Sierpinski's triangle, Koch, snowflake, or Koch curves, they exhibit self-similarity, exact. Another form is self-similarity. Mandelbrot set actually is like the example of quasi-self-similar, because as you know, satellite another thing, see these pictures. These are all examples of fractals in nature. River branches, broccoli, water drops, crystals. See here, this neurons from the human cortex. Lungs even are branching fractals, right? Even brain cells, they are examples of branching of this complex network. This tree, the river network in China, or examples of fractals. The hurricane, even spiral Greek sea. These are examples of fractals. And then you see even this cactus, if you see, that also forms a pattern. Self-similarity is there. Even sunflowers, if you see, pine cones, they are also examples of fractals. I skipped these slides. Even this in Madison, if you see, these are also examples of fractals. So what we say that fractals are all around us. They are in our lungs, they are in our circulatory system, even brains. So if you see here, so Madison also, we see that in bacteria, also in medical imaging, ophthalmology, digestive system, nervous system, so biochemistry. I will show you next slides. These are in architecture also. There are examples of fractals. In Vedic period also, if you see Sudarshan Chakra, Meru, they are all examples of fractals in the Vedic period. Even in architecture of many Indian temples, you see here. This is again the repeated patterns are there. Even if you say it's about its engineering application, if you see in computer chips, in fractal antennas, they're all using this. Even rhythms, they are using Kiosk, DNA, they are using this Kiosk theory when they study DNA. So another thing is fractal curve. So it is a mathematical curve whose shape retains the same general pattern of irregularity, regardless of how high it is magnified. It takes the shape of a fractal, so that's why it is called fractal curve. So some more fractal curves. I skip these because so this is the picture of a dragon curve, if you see. Piano curve, right? So these some example: Kenter set, Sierpinski's carpet, Sierpinski's triangle, Major sponge, Kenter set, T-sphere, dragon curves. These are all fractals. I'm skipping these slides. So if you have these are hyperfractals, the pictures of hyperfractals. Another important part of this is biomorphs also. These are pictures of biomorphs. So several books are there you can find regarding this fractals everywhere, fractals geometry, Kiosk and fractals, fractals and Kiosk. These are good books. Even you have the Dynamics. R.L. Devyani is a very good book. If someone who is really interested in this Kiosk, fractals and dynamics. Even The Symmetry of Kiosk by Gilmore is also a good book. Nonlinear dynamics and Kiosk. I've read this book, Aeon Stewart, Does God Play Dice? The New Mathematics of Kiosk. So you must read this book. I skipped these. So misbehavior of markets. If you see here, that is behavior of markets by B.B. Mandelbrot. That is also about using fractal theory. These are also some. Another is iterative process. I'm skipping this and come to this because iterative processes are used in this. Now come to the third segment and the last segment of my talk, and that is about fuzzy mathematics. Why it all started, how it started and why it started, fuzziness, how it came, how it originated. It's well said by G.B. Shaw that all progress means war with society. कुछ भी नया आता है तो हम उसको एक बार जरूर अपोज करते हैं. आपने देखा होगा जब हम ऑनलाइन forcefully हमने ऑनलाइन टीचिंग को एक्सेप्ट किया. Earlier also it was there. Earlier also webinars were being held. We never tried to attend these. We never tried to have online classes. But when we have some problem or we were in the mid of some issue, when the COVID period started, we were forced to do all these things. And nowadays we are doing this. We have implemented these things in our lifestyle. But earlier we have some you can say, apprehensions about this, how to start it. Same situation was with the fuzzy set theory or fuzzy theory. That's why it was delayed, because people opposed it, that this is not a good thing. Because they always thought that everything is deterministic. There is no such another thing that vagueness is there, fuzziness is there. But if you see in the nature, if you see close to everything, everything is not clear. Everything, there are fuzziness, there are, you can say, vagueness is there. There are situations when they which are not precisely explained, precisely described, then you need this fuzzy set theory. A dictionary meaning of the word fuzzy is problematical, vague, doubtful, not sure, ambiguous. It keeps on varying. Or we can say liable to change. If you see in the dictionary, these are the meanings. Liable to change, not dependence on variable. So fuzzy mathematics, how it started, it was started in 1965 after the publication of L.E. Cheda's paper titled Fuzzy Sets in the journal Information and Control in 1965, where he gave the idea of a fuzzy set. And instead of the crisp set, he gave this idea of fuzzy set. And gave the, earlier we have जनरल कैंटर सेट थ्योरी में जो था आपके पास सिर्फ कैरेक्टरिस्टिक फंक्शन था. That means it was only two valued function. Either it belongs to or doesn't belong to. Characteristic function, if it has value 1 or 0, if it belongs to or doesn't belong to. But now we have the closed interval 0, 1. Now it is a membership function. And it has three stages, how it started the fuzzification of this mathematical concepts. This paper, if you want to further study about this, this is a historical overview of fuzzy mathematics, new mathematics and natural computation by K.E. Mordison and J.N. in 2005. So first how it evaluated? First fuzzy sets were defined, then fuzzy logic and fuzzy set theory, then fuzzy logic controllers were defined in 1974. Then in 1976, first industrial application in Denmark. Then in 1985, Japanese adopted fuzzy control system in their key projects. Even railway system, they accepted this and they adopted this fuzzy control system. What is the basis of fuzzy set theory? Actually, what we have, it is well said by that knowing ignorance is strength, but ignoring knowledge is a sickness. This is the basic of fuzzy set theory. कि आपको नहीं पता, then it's okay. Ignorance तो strength है, but अगर आपको पता है, and you are not going to accept these things, you are not going to implement that things, that is your sickness. So fuzzy set theory or possibility theory, the basis is that you don't ignore knowledge. I skip these things, so I've just given you the idea that L.A. Jeda in 1965, he gave this idea. Here we have, if you see here, another contributor to this theory were Bandler, Dubusis, B.R. Guinness, so many, Henry Perret, R.R. and Z.J. Zimmerman. So if you see the book of Z.J. Zimmerman on fuzzy set theory, it's a good book, very student friendly. And if you are just going to start, then please read this book. That will be helpful to you. So he is well said that L. Jeda in 1965, people don't require precise numerical information input, yet they are capable of highly adaptive control. This is the picture of L. Jeda. He was born on February 12, 1921. He is an American mathematician as well as engineering, and he is known as founder of fuzzy math. And he basically was also electrical engineering. He got this degree from MIT in 1946, then also PhD in electrical engineering from Columbia University. He proposed this theory of fuzzy logic in 1973, and he wrote several books on fuzzy sets, fuzzy logic, fuzzy systems, and selected papers on this. He was also awarded a IEEE Medal of Honor and Benjamin Franklin medal, sorry. So it's instead of two-valued logic system, now we have the closed interval 0, 1. That is, we have infinite valued logical system. I skip and show you the main slides. So this is the main definition of fuzzy set. That means the fuzzy set actually is a mapping from universal set to closed interval 0, 1. And this mapping is called the membership function. And the Cantor set, if you see, is the special case of fuzzy set, because there we have characteristic function. We're having two values, 0, 1. If you see crypt set versus fuzzy set, it has clear boundaries. It doesn't have clear boundaries. Or you can have this black and white. It is black and white. We don't have the gray things here. Here we have gray things here also, because in black and white we don't have always only black and white. We have gray shades also. So watercolorless, Rohit, anyone is, if he is honest, beautiful, or you can say, suppose आप simple example दे सकते हैं fuzziness का. Even stomach ache अब होता है. आप कभी बार बच्चे भी बोलते हैं स्कूल जाने से पहले कि बहुत पेन हो रहा है, stomach ache है, लेकिन आप मेजर नहीं कर सकते. हेडेक हो रहा है, you can't measure कि किसको कितना हेडेक हो रहा है. So that is all fuzziness, right? तो simply beautiful है. आपका perception अलग हो सकता है, मेरा अलग हो सकता है. Honesty जो है, everyone has on perceptions. So यहाँ degree of membership can vary according to your perception. So that is all about fuzziness. If you see here, this has clear boundaries. This doesn't have clear boundaries. I skip this, but one thing I want to discuss, mainly the main important point is here again we have operations, we have relations. Everything is there as the same set theory. I'll show you. But the one thing that is different in this, or one thing doesn't hold good, is this law of contradiction and law of excluded middle. If you see these laws, they doesn't hold good in fuzzy scenario. In fuzzy environment, in probabilistic, they hold good. And there are three different things now we are discussing: deterministic approach, probabilistic approach, and fuzzy approach. Deterministic is the classical approach. Probabilistic you all know. And then this is the fuzzy approach. Here the entirely different scenario is there. So law of contradiction and law of excluded middle doesn't hold good in fuzziness. In fuzzy environment, they doesn't hold good. This is an example, but I skipped this. Sometime we will have a full lecture on fuzzy set theory. But now, because I have to wind up in 5 minutes, I think, Doxima. Oh yeah, no, sorry, I have to take care of this also. So, even also fuzzy set may be continuous or discrete. So fuzzy logic, in the similar way we have, earlier we have Boolean logic. Now we have fuzzy logic, because Boolean, see the pictures of the flowers. Here we have clear boundaries, either belonging or doesn't belonging. Here law of excluded middle holds. But here see these pictures. What about this? We don't have clear boundaries. What to do with that? We don't have belonging or not belonging only. We have different things. So fuzzy logic is a superset of conventional Boolean logic, which has been, why it has been extended? Because the concept of partial truth, or even completely true, completely false, which are fuzzies, that how to measure these concepts, how to implement these concepts, we need this another thing, that is fuzzy logic. So it must have crisp boundary conditions, commutative, associative, idempotent, and monotonic. I'm skipping this, just showing you some pictures. So it all started, if you see how it started, logic, classical logic started in 400 BC, and then 1900. It will have then three-valued logic. Earlier it was two-valued logic, true or false. Then we have in 1900 three-valued logic. But in 65 we have fuzzy logic. That means many-valued, or you can say infinitely valued logic. So application started in 1970, when in Europe applications of fuzzy logic in control engineering was done. Then in Japan, when in railways, they adopted this fuzzy logic system. And then you can say in Europe, empirical verification of fuzzy logic was done in 1980. And then broad application of fuzzy logic in Japan again in 1985. They have accepted these theories and implementing these theories. And 1990 in Europe, again 95, broad applications of fuzzy logic in US were started. In 2000, it became a standard technology. It was applied in data and sensor signal analysis in business and finance. I'm skipping this. One last part is that randomness versus fuzziness, right? This is the question in the universe is basically all about deterministic, probabilistic, or fuzzy. Deterministic was handled by General Cantor as a general set theory. Then probabilistic theory was there. And now the fuzzy theory deals with fuzziness. That is not clarity is there. So there is some difference. If you see the set of women are sitting in a room and next day you want that a beautiful woman are sitting in the room, how they will, the probability will, how many of them will come the next day, that probability theory applies. But it has no concern with the beautifulness of that then. How many beautiful, how they will come, so many will come. That is about fuzziness. So we have that entirely different theories are there. So entirely different meanings are there. And they have, if you see, this is an important slide about various applications of fuzzy logic in engineering. If you see this paper, Fuzzy Logic with Engineering Applications, it's a good book. It's a book by T.J. Ross. I have this book with myself. It's a very good book in John Wiley and Sons in 2005. It has given various applications of fuzzy logic in engineering. So because always it is mentioned in this book that engineering community has mostly relied on earlier probabilistic methods to analyze empirical data. And these methods are used in experiment analysis actually for studying the variation in model parameters, for determining structural properties of various materials and image processing. But these variables, which we consider they are randomly distributed actually. They are randomly distributed and their analysis depends on the methods which satisfies the axiom of probability. But sometimes it happens that you have limited data and it may not be possible to may not be appropriate to use possibility distributions such that complete knowledge is not assumed. So then we need another distributions, that is, or theory possibility distribution. Then they are helpful in these engineering applications. So fuzzy theories about subjective uncertainty, right? Which we can't determine even after the actual things happens. In probability, we have event will happen or not. Here events are there, but the boundaries are not clear, right? So this is the base of fuzzy set theory. Here we have all things possible are not probable, all things probable are possible, and all things impossible are improbable, but not all things improbable are possible. So I will just show you the applications. See this, I'm skipping other. So we have various real life applications, automobiles, vehicle subsystem, cameras. If you see your washing machines, they are using fuzzy logic. Even we have in the video games and pattern recognition, in language filter, traffic lights even, they also use this. Microcontrollers and microprocessors. So this is another paper which deals with the engineering applications. If anyone interested can go through this paper. This is in the Journal Advances in Fuzzy Systems. And because it is well mentioned there, it is fuzzy logic is extremely useful for many people involved in research and development, including engineers, maybe electrical, maybe they are mechanical, they are civil, they are chemical engineers, even they are aerospace engineers, they are they're handling agriculture engineering, they are from the biomedical field, they are from computer field, even in environmental field, geological field, industrial fields. So all these need this fuzzy set theory and fuzzy logic. Even computer software developers, they also need this. I think time is over. Oh, so these are some books on fuzzy set theory. I'm skipping something. So thank you so much for the patient hearing. Or I hope that you were not sleeping or attentively you were attending this lecture. Thank you so much, dear participants. I hope I to impart some knowledge regarding this fractals, chaos, and fuzziness. Thank you so much, everyone. Just 1 minute. Thank you, Doxima. Thank you, Dr. Ekta and organized team headed by our dynamic personality, Dr. Rajeev Kumar, Professor Rajeev Kumar. Thank you so much for providing this opportunity, especially AICT team. I'm thankful for giving us this opportunity that we are handling this 5-day faculty development program. Thank you so much, everyone.
Thank you so much. Now it's time for the Curie session. So anybody, if you want to ask something, then you can write in the chat box, or you can directly unmute yourself and then ask. Anybody? No queries at all? Watching the comments from the participants.
Yeah, I want to watch.
Yes.
Yes, can you show me, Geeta? Can you show me the comments of the, yeah. No. Ekta will provide me.
They all
That.
did the same thing. And one of the participants saying that, can you please share this presentation with us? And sorry for this, the thing, we can't share this presentation as speaker.
Maybe some will try. We will
Share
try.
the video of this lecture. We will upload this video of this lecture on AICT platform. Then you can hear that video.
The voice is not audible, ma'am.
Hello. Video Hello, it's audible now.
Now it's audible.
So I just thank the Professor Renu Chugh ma'am for her erudite presentation, and I'm hoping that this their practical experience and their vast area of research in these fields, in fields of fractals, fuzzy mathematics, going to be very fruitful for you all, because this field is related to all the fields of physical sciences and the engineering technology also. So all the researchers who are working in this field, I guess this is going to be a raw map for them, because she has spent so many years in this area, in this particular area. So thank you so much, ma'am, on behalf of all the organizing team and the convener of this FDP. I again want to thank you for sparing your precious time and knowledge with our participants. Thank you, ma'am. Now, here is a tea break for 15 minutes, and after 15 minutes we will resume back. Attendance link is already shared in the chat box, you can see there. And one announcement for you all is attendance link will be shared in the particular session only. After the session we will not again share the attendance link, so you have to attend the session, and from last 2 sessions we are sharing the attendance link only in the Curie session, but in the next sessions we will not share it in the Curie session. We can share it in between the session or in starting on the session, means at any time of the session. So you have to attend it completely so that you can fill the attendance form, because if you will not fill the attendance form, then it will be, and we will mark you absent, and that will
Excuse me, madam, but I didn't get this. I have attended the whole lecture. I am not getting it in the chat box right now.
ma'am, it
And I
is
have
in the
attended
chat
all
box.
the
It
lectures
is
since
present in
morning.
the chat box. You can see from the name of Dr. Ekta Narwal, you can see the link, attendance link. I have written there that this link is for the second session.
So, madam, can you share it again right now?
Yeah, I'm sharing it again. You can see the chat box. I am sharing it
I am.
again.
Okay.